Hello and welcome to our next lecture. Today we're talking about yet another basis for the space L2. In the last lecture we saw that the real functions sines and cosines make up a basis for the space L2 A to B, and that both types of functions, both sines and cosines, are needed to make the orthogonal set complete. However, if we change a little bit the frequencies of those sines and cosines, we can make it so that only one type of the function is needed to make up a complete orthogonal set. This new basis will be sensitive to the location of the space, so we're going to be talking about the space L2 from 0 to L. So previously for Fourier series, the basis is function 1, function's cosine of 2 pi k over L t, and sine of 2 pi k over L t. If we introduce two new series, cosine series with the basis cosine of pi k over L t, and sine series with the basis sine of pi k over L t. For the cosine basis, k starts at 0 and includes every integer after that. For the sine series, k starts at 1 and goes through all integers after that. So how does that happen? That previously we needed both cosine and sine to make up a complete basis, and now we can get away with just a cosine or just a sine. The big difference is the frequencies at which these functions are oscillating. We're including twice as many frequencies in the sine or cosine series. For now, I want to develop formulas for the coefficients for those series. I'm going to use the standard framework of inner products and the coefficients. So let's assume that there is a function that belongs to space L2 from 0 to L. If we try to use the cosine series for the function f of t, we need to compute the norm squares of each function. And the cases of k being 0 and k being non-zero are different, so I'm going to compute the norm of the function 1 separately from other functions. So this is going to be the integral from 0 to L of 1 squared dt, which integrates to just L. And the norm of cosine pi k over L t squared is going to be the integral from 0 to L of cosine squared pi k t over L dt. And I'm going to compute this norm with the help of Mathematica. So here I have the sine squared and the cosine squared. If I evaluate, then I get that the norm of each is just L over 2, because the sine of 2k pi is always going to be 0 for both formulas, and so in both cases the norm squared of sine and norm squared of cosine is going to be just L over 2. Therefore the coefficients a0 is just going to be 1 over L, the integral from 0 to L of f of t times 1 dt, and the coefficient ak is going to be 2 over L, that's 1 over norm of the function, integration from 0 to L of f of t times cosine of pi k t over L dt. So the function f of t could be represented as the sum. K goes from 0 to infinity. AK times cosine of pi k t over L. And you might say, well, what about the case k equals 0? Well, in that case, the coefficient is a naught, and the cosine is always 1, so the sum works just as expected. It's just we can't have a common formula for a naught and a k because they have a different factor in front of the integral. If we want to compute the sine series, we already computed the norm. That is L over 2, and therefore the coefficient bk is going to be 2 over L integral from 0 to L of f of t times sine of pi k t over L dt. And the function f of t will be just a summation. So k goes from 1 to infinity of bk times sine of pi k t over L. And again, I'm going to turn to my favorite examples, the 10th function and the shifted piecewise constant function. This time I'm going to shift the functions to the interval 0 to 2 because that's how the sine and cosine series work. So the shifted function f of t is now belonging to the space L2 from 0 to 2, and therefore if I want to use the cosine series, then we need to compute the a naught, which is going to be 1 over L, so 1 over 2, the integral from 0 to 2 of the function f of t times 1 dt. Well, this is just the integral of f of t, and the integral is 1 because the area under the graph is exactly 1, so this coefficient is just 1/2. AK we need to be computed as 2 over L, so it's going to be 2 over 2. The integral from 0 to 2 of f of t times cosine of pi k t over L, which is 2 dt. If you compare this formula to the integral we computed in the previous lecture, then you see that the expression inside the cosine has changed. Previously it was just pi kt, now it's pi kt over 2. So let's go ahead and compute those coefficients. I have defined the function, and now it's a shifted function. And now I'm going to integrate the function f of t with the function cosine of pi k t over L, which is 2. And I'm going to integrate for t 0 to 2. As you can see, the formula is quite complicated, so I'm going to compute this formula for several k. So let's call this AK. Let's compute first 15 terms and see what happens. So you can see quite a lot of these terms are 0. First term is 0 because cosine of pi over 2 is 0. The third term is 0 again because of the cosine. The fourth is 0 because sine of 4 pi over 4 is 0. For every odd k, cosine is going to be 0. For every fourth term, sine will be 0. So we can see that only the terms when k is 2 multiple of 4 are non-zero. Just increasing the number of coefficients covered will confirm the pattern. Notice that what we have on the bottom are just odd numbers squared. We have 1 squared, we have 3 squared, we have 5 squared, 7 squared, then 9 squared, etc., etc., etc. So it seems like we can find a pattern to these coefficients. So if you don't mind me to use that pattern, this is what these coefficients are evaluating to. They're evaluating into minus 4 divided by the odd number squared, which I'm going to express as 2j plus 1. squared times pi squared when k is twice that odd number. For the first coefficient we had 1 squared, but the k was 2. For the second coefficient we have 3 squared, but the k was 6, etc., etc. So k should be twice that odd number, and 0 otherwise. Let's see how this cosine series represents my function. So the approximation of f with the cosine series will be 1/2, which is the coefficient a0, plus the sum of ak times the cosine of pi kt over 2. And let's add the first 10 terms. And it looks like it's a nice approximation of my function. If I add more terms, I get a much better approximation of it. So what happens outside of the interval 0 to 2? So let's look at the function plotted from minus, say, 4 to 12. That seems like the function repeats itself. But in fact, it's actually mirror images of this function. Because the function is, we don't see it quite clearly. So the cosine series works, and it works very nicely. Let's do the same thing with the sine series. This time we only need to compute the coefficients bk because k starts from 1. So it's just going to be 2 over L, which was 2, the integral from 0 to 2 of f of t times sine of pi kt over L, which was 2, dt. This time the expression inside the sine is also halved in comparison to the expression we used for the real Fourier series. So if we compute this integral, we'll compute the integral with sine pi kt over L, which was 2. We integrate in terms of t from 0 to 2. Just as before, we get a quite complicated expression. So I'm going to call these coefficients bk and compute a few of them for k going from 1 to 30. This time we see that half of the coefficients is 0, and the coefficients are 8 over 1 times pi squared minus 8 over 3 squared, then we have 5 squared, and we have 7 squared, and the coefficients change sign. Every second of them is negative. We have a positive sign when k is 1 or 5 or 9. So if the distance from 1 is a multiple of 4, then we have a positive sign. If the distance from 1 is not a multiple of 4, then we have a negative sign. So I'm going to exploit this pattern here. I'm going to say that this is -1. I'm going to take k, subtract 1, and divide by 2. So this way, if the from 1 is multiple of 4, this will be an even number, and -1 to the even power will be +1. If k is, say, 3, then this will be an odd power, and this will evaluate to -1. Then there was 8, and there was k squared, pi squared. This is when k is odd, and 0 when k is even. Let's see how this series works for our function. So I'm gonna say that f approximation with the sine series is the summation of bk times the sine of pi kt over 2, and the summation will be for k going from 1 to say 10, and then we'll plot it. For t going from 0 to 2. Not bad either. Including more terms will get us a much better approximation. Let's look at how these approximations get better and better with each term added. Second coefficient was 0, so it's only with the addition of a third term we get a change. Now fourth coefficient will be 0, so let's add 5 terms, 7 terms, 9 terms. It's getting better and better with the addition of each term. So if I add 51 terms, I get a very close representation of my 10th function. 151 terms will make it almost perfect. If we look outside of the interval, then we see an interesting pattern that the function was flipped and turned around. We'll explore that later. Now let's turn our attention to the function g, which is also can be considered as a function from L2 from 0 to 2. If I want to compute the cosine series, then I should start with the coefficient a0, which is going to be 1 over L, the integral from 0 to L, which is again 0 to 2, g of t times 1 dt. But the integral of g of t is 0, so ak is going to be 2 over 2, the integral from 0 to 2 of g of t multiplied by cosine of pi k t over 2 dt. I said previously that because cosine was an even function and g of t was the odd function, this integration is going to be 0, but this time the situation is slightly different. Not only we're shifting everything to the interval 0 to 2, we're including more cosines in this series, so for some of the cosines this integration is going to be non-zero. So let's go ahead and compute it. So again, the function g of t is defined this way. It's from 0 to 2, and it's going first, and it's first jumping to -1, then jumps to 1, then jumps to 0. So if I want to compute the coefficients, then I really need to take the g of t multiplied by cosine of pi k t over L for t going from 0 to 2. Let's call these coefficients ak. Again, let's explore what these coefficients are for a few values of k. Let's see, half of them are 0, and among those that are non-zero, half of them are negative, half of them are positive. So let's compute the approximation. With the cosine series will be defined as sum of a0 was 0. We're going to sum ak multiplied by cosines and let's add first 10 terms. This is what we see. We keep adding more terms, we get better approximations. Again, let's explore how the terms approximate the function one by one. We know half of them are 0, so I'm going to step by 2 terms, 3 terms, meaning 3 non-zero terms, 4 non-zero terms, 5 non-zero terms. It just gets better and better. The progress is less noticeable with each new addition, but you can see how these terms converge to the step function that we have. Adding a lot of terms gives us again the same Gibbs phenomenon where the things oscillate at the discontinuities. Nevertheless, function is approximated quite well. If we look outside of the interval, then all we see is that the function is repeated, but it's flipped around. Let me zoom in to the interval from -2 to 2, then you will see the actual effect. The function was just flipped around in a mirror image around the y-axis. So if you notice the pattern for these coefficients, then these coefficients are, again, I have -1, k minus 1 over 2, 4 over k pi, for k being odd, and 0 when k is even. For the sine series, we compute the coefficients bk as 2 over 2, the integral from 0 to 2 of g of t times sine of pi kt over 2 dt. So we integrate g of t with sine of pi kt over 2. We integrate for t from 0 to 2. Let's call those coefficients bk. Let's compute the coefficients bk for a few values of k. And again, we see some kind of a pattern, and it seems like the k's have been reversed. Now 3/4 of the coefficients are 0, and the non-zero ones correspond to even k's, but not all even k's. It's k being 2, k being 6, k being 10, etc., etc. So if you notice the pattern between 2, 6, 10, it's 2 then every fourth k. So it seems like we have k being 2 plus 4 times an integer. Let's see how well this series represents our function. So the sine series is going to be the summation of the terms bk multiplied by sines of pi kt over 2. And again, let's add just a few terms. When we're adding terms from 1 to 10, only 3 of those terms are going to be non-zero. So we're not actually adding that many terms here. This does look like a function, but I think we need more terms. It's a little bit better. Again, we can see how these functions will represent our function g. The first term is going to be 0, so there is nothing to represent. It only starts with the second term. And then the terms 3, 4, and 5 bring us nothing. So if I add first 5 terms, there's nothing because the coefficients are 0. It's only with the 6 terms that something changes. And with the 10th term, we have a little bit of addition. The 14th term, we have a little bit of change. 18th term, etc., etc. So if I want to add a lot of terms, this is what I get. Notice the difference, that the function actually jumps back to 0. It starts at 0 and jumps back to 0, when our cosine approximation didn't do that at all. It didn't jump back to 0. So if I look outside of the interval, I see a little bit different picture. The function is repeated, but it seems like it's not flipped. But it is mirrored about the y-axis and flipped about the x-axis. We just don't see it here. Just like the last time, I want to consider a different function. So let's go back to our function t e to the minus t, and then compute the cosine and sine series for it. So a naught is going to be 1 over, now I have b playing the role of L, so it's just going to be 1 over b, the integral of the function h of t times 1, and we're going to integrate from 0 to b. Computing the coefficients ak is 2 over b, integrate the function h of t times cosine of pi k t divided by b, evaluated from 0 to b. Let's look how it works. So we're going to add a naught plus the sum of ak times cosines let's add k going from 0 to, let's add the first 10 terms. That looks like a very poor approximation of our function, so adding more terms should fix it. It's a lot better, and this is almost indistinguishable. Let's look what happens outside of the interval. As you can see, the function is just a mirror image of itself. So if I plot from minus b to 3b, then I will see that it's just two of those. So it seems like the function is being flipped around. Then it's treated like a periodic function that has a period from minus b to b. So this is now a 2b periodic copy that is being repeated every 2b interval. Let's try to compute the sine approximation of this function. Computing the series is just going to be the sum of bk times the sines. Again, close, but not that close. Including more terms makes it better. Not so bad, but we can see that the function starts at 0 and ends at 0. And the jump discontinuity that we had at 0 is actually causing the function to have a little bit of a ripple at the end. Again, if I plot the function from minus b to b, then I will see some interesting reflection. So it seems like the function was flipped around the y-axis and then flipped around the x-axis. So it is kind of a rotated by 180 degrees and then attached to the function. So this is how the sine approximations create a 2b periodic copy of the function. And then if I plot from minus b to 3b, then you can see how these things are repeated now. So the sine series expands the function by rotating it by 180 degrees. That way it creates a 2b periodic copy of it, and then it repeats it many, many times. And this difference in the behavior of the sine series and the cosine series is what I want to address now. So suppose we have a function belonging to the space L2 from 0 to L. We can extend the function until minus L to L interval by making either an odd extension or even extension. What are those? So the odd extension and the even extension are doing two different things. So suppose I have a function that looks a little bit like this. Then the odd extension turns the function around by 180 degrees. It creates a copy of the function on the interval from minus L to L. For the even function, the process is different. The even extension of the function extends it by creating a mirror image, and that's how it extends it on the interval from minus L to L. So if I want to write the formulas for this function, then the odd function can be written as f of t for t being from 0 to L, and it's minus f of minus t when t is the interval from minus L to 0. For the even extension, it's again exactly the same as the function for t being from the interval from 0 to L, and it's a mirror image of it when t is the interval minus L to 0. If now compute the standard real Fourier series, for each one of those functions, then I get that a naught is going to be 1 over the length of the interval is now 2L, the integral from minus L to L of the function f odd dt, but I do know that every odd function integrates to 0. For the even function, a naught is 1 over 2L, the integral from minus L to L of the even function. But I know that the integrals of the even function over symmetric intervals are twice the integrals over half of the interval. And what we get here is exactly the formula that I've got for just the cosine series of the even function. Now let's look at the coefficients a, k. There were 2 over length of the interval, the integral from minus L to L of the odd function times cosine of 2 pi k over the length of the interval, 2L. But again, this integrates into 0 because f is odd, cosine is even over the interval from minus L to L, and therefore their product is an odd function. Therefore it integrates to 0. In the case of the even extension, I get 2 over 2L, the integral from minus L to L of the even function multiplied by cosine of 2 pi k t over the length of the interval, which is 2L dt. But again, even times even is an even function, so this is the same as 2 times the integral over the interval to L only, and f even of t over that interval is just the same as f of t. And it seems like this formula is just the formula for the cosine series. Now let's compute the coefficients bk. So I get 2 over 2L, the integral from minus L to L of the odd function of t times sine 2 pi k t over 2L dt. The odd function times an odd function, because sine is an odd function, makes it an even product. And so this integral is the same as twice the integral from 0 to L. But the odd function from 0 to L is the same as f of t. And I got a formula for the coefficient bk for the sine series. Coefficient bk in the case of the even extension is going to be 0. Because the even function multiplied by the sine 2 pi kt over 2l is going to be 0, because the even function times sine is an odd function and it integrates into 0. And therefore the odd function can be written as a summation as k goes from 1 to infinity of bk times sine pi kt over l. And this will represent the function on the interval from minus l to l. But on the interval from 0 to l, this function will be equal to f of t. Therefore, the same series will represent the function f of t on the interval from 0 to l. And the even function is going to be the summation as k goes from 0 to infinity ak times cosine of pi kt over l. Because the bk coefficients for this series are 0, only ak coefficients can integrate into something non-zero. And again, this represents the even extension of the function on the interval from minus l to l. However, the even extension equals to f on the interval 0 to l, therefore the same series will represent the function f of t on the interval from 0 to l. And because this is what's happening behind the scenes when we compute the sine series of the cosine series, we see the effect of the sine series actually creating a copy of a function that has half of it turned 180 degrees, and the cosine series simply flips the image around the y-axis. Because the sine series and the cosine series are actually real Fourier series that we talked about in the previous lecture for even or odd extension of my function f of t here. If you're wondering why do we have so many different kinds of series for the same task, the answer is that the sine series and the cosine series have applications in solving of the partial differential equations, where the solution process naturally leads to the sine series expansion or the cosine series expansion of this. In the next lecture, we're going to consider quarter period series. And those, just as sine and cosine series, also arise from the special cases of solutions of partial differential equations. So the real Fourier series is the universal tool that can represent any real function. And the sine series or cosine series is just a special case of real Fourier series that has its own application within the niche of solving partial differential equations. That's where I'm going to end today. Thank you for listening, and I'll see you in our next video.